Introduction. Students, as we all know that fertilizers are widely used in modern-era agriculture. Fertilizer use has been shown to be very effective in means of increasing agricultural productivity. About 40% of world protein production is based on synthetic ammonia. To meet high demand of ammonia, it is manufactured on large scale by Haber's process. The Haber's process combines nitrogen with hydrogen into ammonia. Nitrogen is an important element in P block in the periodic table. So students, today we'll study about the P block elements. Objectives. At the end of this lesson, you will be able to define P block elements, familiar about group 15 elements, know properties of group 15 elements, analyze anomalous behavior of nitrogen, explain properties and uses of dinitrogen, explain properties and uses of ammonia, understand oxides of nitrogen, explain properties and uses of nitric acid, describe allotropic forms of phosphorus, explain halides and oxides of phosphorus. Definition. Elements of group 13 to 18 of the periodic table are collectively called P block elements. Boron, carbon, nitrogen, oxygen, fluorine and helium head the groups. The general electronic configuration of these elements is Ns2Np1-6. They involve the filling of p orbitals of their outermost shell. The maximum oxidation state shown by a P block element is equal to the total number of valence electrons. This maximum oxidation state is called the group oxidation state. Group 15 elements, the nitrogen family. The elements nitrogen, phosphorus, arsenic, antimony and bismuth constitute group 15 of the periodic table. The first two elements of this group, nitrogen and phosphorus, are non-metals. The next two, arsenic and antimony, are metalloids. The last element, bismuth, is a metal. All the elements of this group have 5 electrons in their valence shell. Their general valence shell electronic configuration is Ns2Np3. Physical properties of group 15 elements. Atomic radii. It increases with increase in atomic number. Melting point and boiling point. These increase on going down the group. However, the melting point of bismuth is usually low. This may be due to more tendency of bismuth to form 3 rather than 5 covalent bonds. Thus, there are weak forces of attraction between their atoms in solid state responsible for its low melting point. Density. The density of the members increases down the group. Ionization enthalpy. The first ionization enthalpy decreases regularly down the group due to increase in the size of atoms and screening effective of intervening electrons. Repeat. And screening effect of intervening electrons. General characteristics of group 15 elements. Catenation. The elements of group 15 also exhibit catenation. Nitrogen forms chains extending up to 3 atoms. Phosphorus shows a distinct tendency for catenation, forming both cyclic and open-chain compounds containing several phosphorus atoms. Allotropy. Except nitrogen and bismuth, all other elements of the group show allotropy. Phosphorus exists as white, red, and black phosphorus. Arsenic exists as yellow and grey. Antimony exists as yellow and grey. Electronegativity. The electronegativity value decreases down the group with increasing atomic size. Oxidation state of group 15 elements. All the elements of this group have 5 electrons in their valence shell. These elements require 3 more electrons to acquire noble gas configuration. But gaining of 3 electrons requires a large amount of energy. It takes place only with nitrogen, as it is the smallest and the most electronegative element of this group. The other elements of the group form covalent compounds in which their formal oxidation state is -3. The elements of this group also exhibit +3 and +5 oxidation states, but they cannot form M5+ ions due to the large amount of energy required. Most of the other compounds with +3 and +5 oxidation states of these elements are covalent. In the case of nitrogen, all the oxidation states from -3 to +5 are possible. Anomalous behavior of nitrogen. Nitrogen differs from rest of the members of the group due to its small size, high electronegativity, high ionization enthalpy, non-availability of d orbitals. Nitrogen has the unique ability to form pi-pi multiple bonds with itself and with other elements like carbon, oxygen having small size and high electronegativity. Thus, nitrogen exists as diatomic molecule with a triple bond between the two atoms having high bond enthalpy 941.4 kJ per mole. Single nitrogen-nitrogen bond is weaker than single phosphorus-phosphorus bond because of higher inter-electronic repulsion of the non-bonding electrons owing to the small bond distance. Hydrides of group 15 elements. All elements of group 15 form hydrides of the type MH3. Structure. All these hydrides are covalent and involve sp3 hybridization. 3 of the 4 sp3 hybrid orbitals overlap with 1s orbitals of 3 H atoms to form 3 MH sigma bonds, while the 4th hybrid orbital contains lone pair of electrons. The bond angle decreases down the group. Basic character. Due to the presence of lone pair electrons on the central atom, these hydrides act as Lewis base. Electron density around the central atom decreases down the group. Hence, the basic character of these hydrides decreases down the group. Thermal stability. The stability of these hydrides decreases down the group. This can be explained in terms of their bond dissociation enthalpy, which decreases down the group. Boiling point. The boiling point of these hydrides first decreases and then increases down the group. The variation in boiling points is due to hydrogen bonding and van der Waals forces of attraction. Oxides and halides of group 15 elements. Oxides. All members of the group generally form oxides of the type M2O3 and M2O5. the acidic character of the oxides decreases down the group. N2O3, P2O3 and As2O3 are acidic in nature. Sb2O3 is amphoteric in nature. Bi2O3 is basic in nature. Halides. These elements react with halogens to form two series of halides: trihalide and pentahalide. Trihalides of these elements, except those of nitrogen, are stable. Nitrogen does not form pentahalide due to the absence of d orbitals in its valency shell. Pentahalides are more covalent than trihalides. Dinitrogen. Dinitrogen constitutes about 78% of air by volume. Relatively little nitrogen is found as compounds. Some preparation methods of dinitrogen are the following. Dinitrogen is produced commercially by fractional distillation of liquid air. Liquid dinitrogen with a lower boiling point, 77.2 Kelvin, distills out first, leaving behind liquid oxygen. In laboratory, dinitrogen is produced by warming a concentrated solution of ammonium nitrite. Dinitrogen is collected over water. Dinitrogen can be produced by heating a mixture of NH4Cl and potassium dichromate. Very pure nitrogen is obtained by heating sodium azide or barium azide. Properties of dinitrogen. Dinitrogen is a colorless, odorless and tasteless gas. It is relatively insoluble in water. It is a non-poisonous gas. It neither burns nor supports combustion. It is chemically inert at room temperature, but its reactivity increases rapidly with an increase in temperature. At very high temperatures, nitrogen combines with some of the more active metals to form nitrides. At very high temperature, nitrogen combines with nonmetals. Uses of dinitrogen. The important uses of dinitrogen are the following. It is used in canning foodstuffs. It is used in manufacture of NH3 and calcium cyanamide. It is used as a refrigerant to preserve biological materials and in cryogenic studies. It is used to provide inert atmosphere in welding. Ammonia. Ammonia is present in small quantities in air and soil where it is formed by decay of nitrogenous matter. In laboratory, ammonia is obtained by heating an ammonium salt with an alkali. Ammonia is dried by passing over quicklime. On a large scale, ammonia is manufactured by Haber's process. The Haber's process combines nitrogen from the air with hydrogen derived mainly from natural gas into ammonia. The reaction is reversible and the production of ammonia is exothermic. A pressure of above 200 and temperature of 700 Kelvin and the presence of catalyst favors the formation of ammonia. Properties of ammonia. It is a colorless, pungent-smelling gas. In the solid and liquid state, it is associated via intermolecular hydrogen bonding and has higher melting and boiling points. Due to the presence of lone pair of electrons on the nitrogen atoms, it is a Lewis base. It has a trigonal pyramid structure. N is sp3 hybridized and the bond angle is 107 degrees. It has 3 bond pairs and 1 lone pair of electron. It is highly soluble in water and is weakly basic. It can form coordinate covalent bond with the transition metal ion and form complexes. Uses of ammonia. The important uses of ammonia are the following. It is used as laboratory reagent and solvent. It is used in industry to manufacture fertilizers. It is used for nitriding of steel to produce very hard surface. Liquid ammonia is used in refrigeration. Oxides of nitrogen. Nitrogen forms a number of oxides in different oxidation states. Nitrous oxide or nitrogen 1 oxide. It is prepared by cautiously heating NH4NO3 or a mixture of NH4Cl and NaNO3 to about 500 Kelvin. Pure N2O is obtained by warming a mixture of hydroxylamine, hydrochloride and NaNO2 solution. It is a colorless gas with sweet taste and pleasant smell. It is also known as laughing gas. A mixture of N2O and O2 is used as an anesthetic, particularly in dental surgery. Nitric oxide or nitrogen 2 oxide. It is obtained by reducing HNO3 with ferrous ions. It is a colorless, poisonous gas. It readily gets oxidized to brown-colored NO2. It acts both as an oxidizing agent and reducing agent. It is neutral oxide and paramagnetic. Dinitrogen trioxide or nitrogen 3 oxide. It is obtained by cooling an equimolar mixture of NO and NO2 to 253 Kelvin. It is a blue liquid. It is very unstable and exists only in the liquid state. It is an acidic oxide. It neutralizes alkalis to form salts called nitrites. Nitrogen dioxide or nitrogen 4 oxide. It is prepared by heating lead nitrate. It can also be prepared by reduction of concentrated HNO3 by metals. It is a brown-colored gas. It turns to colorless N2O4 at low temperature. It is acidic in nature. Dinitrogen pentoxide or nitrogen 5 oxide. It is obtained by dehydration of concentrated HNO3 by P4O10. It is a white delicescent solid, acidic in nature. It is unstable above 243 Kelvin. It is a very strong oxidizing agent. Many organic substances burst into flames in coming in contact with it. It is an acidic oxide. It is anhydride of nitric acid and forms salts called nitrates. Nitric acid. In laboratory, nitric acid is prepared by distilling a mixture of NaNO3 or KNO3 with concentrated sulfuric acid at 573 Kelvin. On large scale, nitric acid is manufactured by Ostwald process. For example, conversion of milk into curd by lactobacilli enzyme present in curd. Ostwald process. Ammonia is mixed with air in 1:8 and passed over platinum gauze at 1093 Kelvin. NO and NO2 thus formed are absorbed in water to get diluted HNO3. It is then concentrated by distillation up to 68% by mass. Further concentration up to 98% is achieved by distilling it over concentrated H2SO4. Properties of nitric acid. It is a colorless fuming liquid, somewhat unstable, and quickly turns yellow due to NO2 produced by its partial decomposition. It has corrosive action on skin and turns the skin yellow. It is a strong acid, forms nitrates with bases and basic oxides, and decomposes carbonates. It is a strong oxidizing agent, oxidizes metals, nonmetals and metalloids into their oxides or oxoacids, and itself gets reduced to NO2, NO, N2O or NH3 depending upon the nature of the substance oxidized, concentration of the acid and temperature. Uses of nitric acid. The important uses of ammonia are following. It is used in the manufacture of dyes, drugs and perfumes. It is used for purification of silver and gold. It is used for etching designs on copper, brass and bronze. It is used as an oxidizer in rocket fuels. It is used in the manufacture of explosives. It is used as laboratory reagent. The major use of nitric acid is in the manufacture of ammonium nitrate. Phosphorus. Phosphorus occurs largely as phosphate rock or phosphorite. It is never found free in nature. Bones have a high percentage of calcium phosphate. The phosphate ore is heated with sand and coke in an electric furnace at 1773 Kelvin. The volatile P2O5 formed is reduced by coke, and the vapors of phosphorus are condensed under water to give white phosphorus. Allotropic forms of phosphorus. Phosphorus exists in three types of allotropic forms: white phosphorus, red phosphorus, and black phosphorus. White phosphorus. It is a translucent white waxy solid. It is insoluble in water and does not react with it. It is poisonous and causes decay of jaw bones. It has tetrahedral structure with a bond angle of 60 degrees. Due to angular strain in P4 molecule, white phosphorus is quite reactive. Chemical properties. White phosphorus gets readily oxidized in air. It reacts with hot concentrated NaOH to form phosphine. It combines with chlorine to form PCl3 and PCl5. It burns brightly in air, producing dense white fumes of trioxide and pentoxide. Red and black phosphorus. Red phosphorus. It is obtained by heating white phosphorus at 573 Kelvin in the absence of air for several days. Properties. It has iron-grey luster. It is odorless, non-poisonous and insoluble in water. It has high ignition temperature of 533 Kelvin and does not show phosphorescence. Chemically, it is much less reactive than white phosphorus. It is polymeric, consists of chains of P4 tetrahedra linked together. Black phosphorus. It has two forms. Alpha black phosphorus. It is formed when red phosphorus is heated in a sealed tube at 803 Kelvin for sufficiently long time. It is a very stable allotrope and does not oxidize in air. Beta black phosphorus. It is obtained by heating white phosphorus at 473 Kelvin for several days in presence of mercury, which acts as a catalyst. It is crystalline in nature with a sharp melting point of 860 Kelvin. It is also very stable and does not burn in air even up to 673 Kelvin. Phosphine. Phosphine is prepared by boiling white phosphorus with 4% NaOH solution in a flask from which air has been displaced by passing oil gas. Oil gas is continuously bubbled through the flask in order to displace air. pH3 contains considerable amounts of H2 and little P2H4 and is inflammable in air. Impure phosphine bursts into flames as it comes in contact with air and forms vortex of white rings of P4O10. Pure phosphine, which is not spontaneously inflammable, is prepared by warming phosphonium iodide with caustic potash solution. Properties of phosphine. It burns vigorously in air to form P2O5 but is not spontaneously inflammable when pure. It is sparingly soluble in water and does not react with water. It is a colorless gas with a very unpleasant smell of rotten fish and is poisonous. It decomposes when heated to 717 Kelvin. It precipitates copper as copper phosphide as free metals when passed through their solutions. It is less basic than NH3, therefore reacts only with strong acids. Phosphorus halides. Phosphorus forms two types of halides: phosphorus trichloride and phosphorus pentachloride. Phosphorus trichloride. It is prepared by heating phosphorus in a current of chlorine. It can also be prepared by action of thionyl chloride on phosphorus. It is a colorless mobile liquid with a pungent smell. The molecule has pyramidal shape. It readily fumes in moist air and violently reacts with water. It reacts with organic compounds containing OH group. Phosphorus pentachloride. It is prepared by the action of dichlorane on PCl3. It is prepared by the action of white phosphorus on thionyl chloride. It is yellowish crystalline solid with pungent odor when pure. It violently reacts with water first to give POCl3, which finally gives phosphoric acid. It gives chlorides when heated with corresponding finely divided metal. Oxoacids of phosphorus. Phosphorus forms a number of oxoacids. The important oxoacids of phosphorus are the following. Orthophosphorus acid. It is prepared by dissolving P4O6 in cold water. It is readily obtained by the reaction of PCl3 and water. It is a white deliquescent solid. It is a dibasic acid. It has strong reducing properties. It precipitates silver from their salt solutions. Orthophosphoric acid, H3PO4. It is prepared by dissolving P2O5 in water. It is also prepared by the action of diluted H2SO4 on rock phosphate. It is a colorless crystalline solid. It is externally deliquescent and absorbs water, giving syrupy phosphoric acid. It is a tribasic acid. On heating, it progressively loses water molecule to give pyrophosphoric acid at 523 Kelvin and metaphosphoric acid at 873 Kelvin. It reacts with AgNO3 solution to give a yellow precipitate of AgPO4. Phosphoric and metaphosphoric acid. Phosphoric acid. It is obtained by heating orthophosphoric acid between 473 to 523 Kelvin. It is a white crystalline solid and tetrabasic in nature. On strongly heating it, it loses a water molecule to give metaphosphoric acid. Metaphosphoric acid. It is prepared by dissolving P2O5 in cold water. It can also be prepared by heating H3PO4 to 873 Kelvin. It is a deliquescent solid. It does not exist in monomeric form but as polymetaphosphoric acid HPO3N. It is a monobasic acid. Did you know? Nitrogen was discovered by Daniel Rutherford in 1772. The name phosphorus originates from the Greek word phos, meaning light, and phorus, meaning bearer. The 6 elements of nitrogen family together make up less than 0.2% by weight of the Earth's crust. Summary. Let us summarize what we have learned. The elements nitrogen, phosphorus, arsenic, antimony and bismuth constitute group 15 of the periodic table. They have 5 electrons in their valence shell. Their general valence shell electronic configuration is Ns2np3. The electronegativity value decreases down the group with increasing atomic size. Due to the presence of lone pair electrons on the central atom, hydrides of group 15 elements act as Lewis base. Nitrogen does not form pentahalide due to the absence of d orbitals in its valence shell. The Haber's process combines nitrogen from air with hydrogen derived mainly from natural gas into ammonia. White phosphorus is a translucent white waxy solid. It is insoluble in water and poisonous in nature. Phosphorus trichloride is colorless mobile liquid with a pungent smell. The molecule has pyramidal shape. Phosphorus pentachloride is yellowish crystalline solid having pungent odor in pure state.